Here. So, good afternoon, everyone. I'm Pakum Sapsunthorn from the ND Lab, Stanford Bioengineering. And today I will talk about our attempt to build a bigger and better storage device that can operate inside the living cell. So, why do we care about that, right? So, there are at least two main applications that we are thinking about when we start the project. So, one is to use this storage device as a tool for studying biology, as something that allows us to relate the history of the cell to the phenotype of interest. For example, you may ask the question of how many times the cell has been dividing, or what are the series of inducer that the cell has been received during the process of differentiation or development or cancer development or whatever. Another area of application is to use it as a tool for engineering a complex behavior. Imagine that if you want to engineer a smart microbe that can swim around 3 times, jump around twice, and then explode, for example, right? You need some kind of capability that you embed inside the cell that allows it to remember what has it done in the past. And again, you need some kind of memory. If you think about the smallest unit of memory, a single bit, you can encode it in the epigenetic level using some kind of feedback loop, let's say some gene A that activated the cell, right? It can be in the off state in which the expression is low, and if you have some input of interest that can trigger expression of A, turning it on, all right? And because A activated itself, so when you remove the input, A keeps the memory of what it has been exposed to in the past. Another way of doing it is to put it in the genetics level. So you have some kind of DNA inside the cell, and you change it by mutation or rearrangement of some kind. And then, once the cell grows and divides, this information is passed on to the next generation. So, on the left-hand side, you have one disadvantage, which is volatile memory, in the sense that you need to spend some energy, some resources, in this case, to keep expressing gene A to store the memory. On the other hand, on the right-hand side, you pass along the information passively in your genome or in your DNA. All right, you can kill the cell, you can freeze the cell, fossilize it, take DNA out, you don't lose the information. So we focus on this. Let me give you a specific example of what we have done in the past. So here is a DNA inversion, DNA-based storage device. So the black line that you see here represents a piece of DNA. The two triangles is a specific recombination site for the enzyme that called FIMP. And you have some promoter here in the middle between the recombination site. The input of interest is supposed to induce expression of the enzyme FIMP. So the enzyme comes in and flip this piece of DNA and turn on the gene downstream. Okay? And so because of that, even after the enzyme is gone, even after the inducer is gone, you still have the downstream gene, the GFP here, keep expressing. So the system can keep a single bit memory of whether or not it has been exposed to the inducer of FIMP. People have tried to build something that even more complicated than that, try to scale it down. For example, in this case, people try to build the 3-state counter using this kind of 2 DNA inversion in the row. And in this case, they use the arabinose induction to flip the 2 inversion bits successively. And they use 2 different enzymes, FLP and PRE here, as a mechanism for flipping the piece of DNA. And so here, with this system, when they induce it with arabinose, first pulse, second pulse, nothing happens. When the third pulse comes, you turn on the gene downstream. Okay. So even though this is one of the best devices that has been built so far, it can only go up to 3 states. And another limitation is that it's not so robust. So it actually showed in this particular paper that when they vary the gap or the width between the pulse just a little bit, the system failed. So the efficiency window is really narrow. Okay. So if you look at the application and where we are right now, right, we've got kind of 3-state counter. It's not so robust yet. And the exciting application that I talked about early on, let's say to track the lineage of the cell or number of cell division, is actually pretty far off. You need like 10 states or like hundreds of states. So it's order of magnitude off from where we are right now. So the goal of our research from the beginning is to try to close this gap. And I will talk about these 3 major progress that we made recently. starting from the first one, which is rewritable genetic data storage device. Okay. So if you recall a few slides ago, I talked about volatile and non-volatile memory as an advantage and disadvantage of these two types of storage devices. So this one is advantageous in the sense that it doesn't consume that much energy, so you can put many of them inside the cell without sucking up too much resources. Here you need to express, each bit, right? And so here might be better for scaling up. But there's one limitation, because in this case, you can imagine that you can erase the state. For example, by having some input that kind of turn A off, right? And you can go back to the off state again. But here, to reverse the mutation completely, or to reverse the recombination process, it's pretty difficult, and it's the area that is underexplored. And so the work that we just got published a few months ago, we actually focusing on using a factor to control the directionality of the combination, so that we can do DNA level storage that is rewritable. Okay. So how does it work? We use a system that we actually borrowed from the bacteriophage virus. Some of these viruses had a capability to insert genome into the host genome whenever the condition of the host is not good for viral replication. So you have the virus DNA here and the host DNA here. And it uses an enzyme called integrase that can go to the specific site on the virus DNA called the P site, recombine with the B site, which is the specific sequence on the bacterial host cell, and recombine these two sites together, get the site that we call L and R, and insert this virus DNA into a piece here that we call a protein. Alright. Whenever the condition is good, you can reverse this process using the same enzyme integrase and another cofactor protein that we call excisionase. So the virus can pop up, start replicating, and kill the host cell. So the basic idea behind our rewritable memory is actually apply this system in a different context. So it's almost the same, but we share the topology of the site rearrangement such that the integrase and excisionase action result in the inversion and the reversion of a piece of DNA. So it's just like the first example of the inversion storage device that I showed you earlier on. But here, you have the mechanism to go back. So let's see in detail how it works. Right? So here, in schematic drawing, we have these site for the integrase embedded in the chromosome of bacteria, in this case the E. coli cell. Have the promoter in between here to driving the downstream device. We have the integrase gene that function for the set, and you have the integrase excisionase polycystron to function as a reset. Right? And to see what is the state of the device, so we also put the fluorescent protein downstream here on the two sides. And to control whether or not they express this upper branch or the lower branch, we also put some inducible promoter upstream here, which is in this case the ATC and arabinose inducible promoter. Right. And so how does it work? So let's say we start from the LR state. Right. The promoter pointing down toward IFP. So if you read out the GFP level here, this is the flow cytometry result of the bacterial population. You see that the GFP level is pretty low because we didn't express GFP here. Right. And so when we induce it with arabinose, so we express both integrase excisionase, so we combine the LR site to the BP site, and you see that the GFP level going up. Okay. Now when we remove this inducer, what happens is that we no longer have the enzyme, but because this DNA here already changed, so it can stay there in that state and pass along to next generation. So after we remove, we can hold this high GFP state until we induce it again with the ATC. So in this case, we can bring all the integrase out, and we combine these two sides get back to the LR state. And so the GFP level coming down again. All right. And again, because it's on a DNA piece, right? So the cell go and divide it and keep that state in the lower GFP state until we start repeat the cycle again and again and again. So we have shown that we can repeat it up to 8 to 10 cycles at least, and we haven't seen any change in performance yet. So it's pretty robust, and it's the first rewritable memory that has been demonstrated. And there are other few things that I would like to point out about the strength of this system. So the first thing is that you can kind of see the modularity of the system here.